Okay, so now we're going to talk about Keras. Keras is a API that's designed for human beings, not machines. Basically, it's designed to make the user experience much better. It allows you to go from an idea to a concept very quickly. So what does it mean? So for example, if I have a deep learning model I built using TensorFlow, it might take 42 lines of code. I can develop the same model using Keras in 11 lines. So think about the power in doing that. You're able to say, okay, we're going to shrink this down. It makes it so it's much easier, far more robust. Plus, you have wide industry adoption. Keras has strong multi-GPU support. It supports a number of different backend engines. You could run a Keras model on a TensorFlow kernel or Theano kernel as well. It's just a great experience for deep learning, and we're going to build a few models using it. Machine learning, we've gone through a few examples, but one of the things that's important is understanding that supervised machine learning is the process of mapping an input to an output based on examples, right? So you feed a model a number of examples, you allow the examples to have labels or labeled training data. And all labeled training data is it infers a function from labeled training data consisting of a set of training examples, right? So recession data, you have zeros and ones, and zeros meaning no recession, one meaning recession. With those labels, you can say that given these economic conditions, now we can learn what a recession looks like. And that's basically all it is. You have a set of labels, then you have a supervised machine learning task. Data modeling. So that consists of 4 different items: data transformations, which is just the transformations needed to make sure your data is ready before feeding it to an algorithm. Standardization, we talked about that as well, which is a common requirement for any machine learning estimator. And we discussed how different transformations and standardizations can affect a model. So, for example, normalization versus min-max scaling, or normalization versus standardization. And also various built-in functions that really make your life easier. So sklearn.preprocessing is something that's really helpful, and we did a few lessons using that as well. And scaling, again, making the differentiation between standardization, which is looking at data based on standard normal units, and then scaling it, or scaling it between 0 and 1. And we saw in the previous lectures what that does in terms of the predictive power of your models. Data modeling. So from an unsupervised learning perspective, we're really talking about factor shrinkage methods or clustering models. So in other words, if you have a data set and you really don't know what's there, but you want to understand what the patterns are within that data, the first thing you're going to need to do is to normalize or standardize that data so that everything is within a similar scale. Then you look at how the data is grouped together, and that's what clustering does. Clustering association allows you to really understand how data moves together, and you could partition various clusters, and we showed you how to do that using the ELPO method to determine how many clusters you should use for your analysis. Okay, and again, unsupervised learning is essentially saying that you don't have to provide your model with labeled examples. Visualizing data, we talked about that as well. So you really want to understand what types of visualizations you need. So are you making comparisons? Are you looking at distributions? Do we have outliers in the data? Is there a trend? Is there seasonality? What types of relationships are there? So think about it this way: when you're looking at relationships to determine if there's strong correlation, you probably want to think about a heat map, right? That way you can see in one grid all the different relationships, and you can see, is there multi-collinearity, or are the relationships, is there strong correlation between the different factors inside of your model? And if that's the case, then you want to have some sort of control for that, either in your regression, or maybe you want to run a principal component analysis to reduce the number of features into their orthogonal roots. Also, if you have trend or seasonality, then perhaps you want to look at a time series plot as well. And if you're making comparison of the different data sets, or let's say, for example, you're looking at distributions of the data sets. So one thing we looked at was the distribution associated with the residuals in a regression plot, right? So we want to look at those residuals, make sure that we are normalizing the data so we can see if there's any trend in the data. Do the residuals look like they approximate a normal distribution? If they don't, then we may need to make an adjustment to how we are pre-processing that data. Okay. Matplotlib. So we've talked about that as well. So we actually used it in the previous lectures. And Seaborn, we use that for our heat maps. Plotly is something that you can test on an open source basis. It's very similar to Seaborn, but they have some really interesting user interaction features that are great. And you do have to pay for some of the more advanced features. And QuickSight is Amazon Web Services visualization package. It allows you to perform many of the same functions you're seeing here with some of the other visualization packages, including Matplotlib, but you're looking at data in real time. So I think of it as how do I put this? A slightly more user-friendly version of Tableau, and a bit less expensive as well. So with that being the case, it's still, any one of these packages work really well for what you're trying to get done. It just depends on what you're trying to do. So if you're trying to put something in a production environment and you would like to look at real-time models, then I would say AWS QuickSight makes the most sense. If you're trying to design something for sharing with other people on your team, then you might want to use Seaborn or Matplotlib. And again, Amazon QuickSight, very, very strong model package where you can even run regressions inside of a QuickSight. So you don't necessarily have to be an advanced data scientist in order to use it. I think it offers a really compelling alternative to Tableau. I've used it a few times in the past, and the setup is really similar to Tableau. But again, you can use it to look at real-time data. You can also run regressions and perform other advanced statistical analysis right inside of QuickSight. Algorithms, so regression, classification, PCA, naive Bayes, text analytics. We've covered almost all these topics with the exception of text analytics, and we will do that going forward. Regression analysis, that's just finding the slope of a line. We did that in a previous lecture. Y equals mx plus b, right? Everybody knows that from high school algebra. And of course, it can be much more complicated than that if you're looking at multivariate stepwise regressions, or you're saying, hey, we're trying to explain a linear relationship or nonlinear relationship for that matter, using a feature-rich data set with maybe hundreds of different factors that you're using to explain your y variable. Regression analysis is the cornerstone of machine learning. Everything pretty much starts here. So you'll have linear regression, or if you want to take the data so you can perform a classification task, if you will, you could use logistic regression, which is essentially the same equation, but you're just putting it on a log scale. And here is the equation, y being a predictive value, the regression equation. It's just the slope of a line, y equals mx plus b. And of course, if you use more factors, then this equation will expand a bit. And a linear regression, again, is just an approach for modeling the linear relationship between two variables. You have linear, logistic, nonlinear regression, and ridge regression. Ridge regression is, we also showed you that as well. That's just a type of regression that can be used for sparse data sets, and it basically uses a type of penalization, an L2 penalization or L1 penalization on that data to reduce the effects of that, of overfitting and things of that nature. So again, so specifically you use ridge regression if you have a really large feature matrix and there's some multi-collinearity, and you want to make sure you're penalizing the regression to account for that multi-collinearity. Classification. So classification, we talked about that as well. So when you, for example, if you're assigning labels to a training set, and these are not continuous values. So, for example, a 0 or a 1, or spam or not spam, or um, fake news versus non-fake news, right? These are different types of classifications that you're using. Or, for example, let's say you are using a convolutional neural network and you're trying to predict a different types of animals that are being seen inside of an image. So you're effectively classifying different animals based on the images that are being received by the model. And again, we talked about classification, spam, not spam. It's classification is a type of supervised learning. A common technique used for classification is KNN. We also use decision trees and naive Bayes. Principal component analysis is a type of analysis in which you, let's say, for example, you have a large number of features, and many of these features are correlated with each other. One of the things you do is you'll use factor shrinkage methods like principal component analysis to maintain the core volatility of those features, but reduce the number of factors that you're using. So imagine if you just have 10 factors, you could probably go ahead and run your analysis on those 10 factors and say, okay, well, I'm able to get this done efficiently and it's tractable because you understand what each component means and you're able to explain your Y variable. You can't really do that if you have 10,000 factors. So, or more. So principal component analysis allows you to shrink the number of factors that you are using into their latent feature vectors. And then you can use those orthogonal factors inside of your regression. And that makes it so you're getting significant speed ups in terms of the processing of your data, but at the same time, you solve the multi-collinearity problem. Okay, so again, when it comes to principal component analysis, it's fast, really flexible. It's a factor shrinkage method, orthogonal transformations, meaning the different features that are remaining are not correlated with each other. And you get speedups in terms of the amount of time that it takes to run your analysis and run your computation simply because you're doing it on a smaller number of features. Natural language processing will be the next section that we cover, and we'll be right back after a break.